So we're going to talk a little bit about series and parallel circuits. And whenever we do this in class, we did this activity in class here, and very often what ends up happening when we do an activity like this in class is that people get a little bit lost along the way, and so we're going to recap and make sure that everyone is on the same page. So we're going to go through this relatively quickly because we've seen a lot of this in class already. So first of all, we want to remember that with current, when we're talking about a series circuit, current is the same at each load. Okay? And in a parallel circuit, then when we have multiple paths, current is split between the loads. Okay? Voltage is not the same story. In a series circuit, we have to split the voltage between the loads, and we would have learned that, we would have seen that explicitly when we did our lab a couple of days ago. But in a parallel circuit, voltage is going to be the same at each load. Okay, so each branch gets the same amount of current. Okay, so here is an example of a very simple series circuit. We've got lamps 1, 2, and 3. We've got a battery, and we're told that the current coming out of the battery is 2.5 amps. Okay, so first of all, the voltage, just to recap for all of us here, the voltage of a standard AAA battery is 1.5 volts. Okay, so this, we should be calling this an electrochemical cell. So just one of them is an electrochemical cell. A battery is a collection of electrochemical cells, and in this case, when we look at this, we've got 1, 2, 3, 4, 5, and 6 of them. So then 6 electrochemical cells times 1.5 volts each is equal to a total of 9 volts. Okay, so that's what this battery is supplying. It's a 9-volt battery. And let's get into some of these questions. What is an alternative form, an alternative term for potential? So I just gave it away. For voltage, and that would be electric potential. How are these 3 lamps connected? Well, because they're all in a straight line, there's nowhere for the electrons to go. We know that they are connected in series. What is the voltage across lamp 1? Well, in this case, if I've got 9 volts and these lamps are all identical, they have to be, voltage is of course going to be split. You're going to get 3 volts here, you're going to get 3 volts here, and you're going to get 3 volts here. And that's just the way it works, because we know that in a series circuit, we split our current up, our voltage up. So what is the voltage across lamp 1? 3 volts. And our reasoning is because in a series circuit, voltage is split. All right. What is the current through lamp 1? Now don't let this throw you. We've been told that the current coming out here is 2.5 amps. Is there anywhere for these electrons to go other than in the path that's provided? And the answer you should be saying is no, there's nowhere else for them to go. It's a series circuit. And that means that we would say then that the current, not just through lamp 1, but through every single point in this circuit, no matter where we measure the current, we're going to get the same 2.5 amps. And the reasoning for that is because in a series circuit, current is the same everywhere. All right. So then what's the current through lamp 3? Well, 2.5 amps. Why? Ditto. Same reason as above. What happens if lamp 2 burns out? Well, we know this well now because we've tested it. We've actually done this experiment, and it means if lamp 2 burns out, all the lamps go out. And that's important because in a series circuit, when one lamp goes out, they all go out. It's one of the drawbacks of wiring in series. All right, so here we tried to build this. We used a 6-volt battery. All the lamps are identical. And we would have measured differing currents across lamp 1. But this is what we're going to say. We're going to say we use the supplied equipment. We got 6 volts of battery. The lamps are identical. And we're going to say that the lamp 1 had a current of 0.5 amps is what was going to happen. Okay, so that's what we got, 0.5 amps. We're going to answer the question. We're going to verify our response. So there are 3 routes for electrons to travel. Down here, and then down here, right? So these are the 3 routes that our electrons can travel in this circuit. But what are these routes called? And we call these, of course, branches. Okay, so in an electric circuit, the routes that electrons travel in a parallel circuit they're called branches. Okay, so let's mark the positive and negative terminals on the battery. So we know that the long line is the positive and the short line is the negative. And so this is done. Indicate the direction of electron flow. Well, obviously electrons are going to flow away from the negative terminal and then towards the positive terminal. And so this is good. All right. What is the voltage drop across lamp 1? Well, if this right here is a 6-volt circuit, we know that in parallel, voltage is going to be the same across each branch. So it means this branch here is going to get the same as this branch here, which is going to get the same as this branch here. And the reason that we know that is because that's the rule for parallel circuits. So if we're using a 6-volt battery to do this, then it means each branch gets 6 volts. So what's the voltage drop across lamp 1? It's 6 volts. And that's because in parallel, each branch gets the same. And we would have verified that. Okay? What's the voltage drop across branch 3? So here's branch 3. It's this guy right here. It's the same thing. The voltage drop here is 6 volts, and it's for the exact same reason. Each branch gets the same thing. Okay? Which lamps work when lamp 2 goes out? So this is the nice thing about parallel circuits. In this one, you totally would have seen when you wired this up. If this guy right here goes out, current can still flow here through this lamp, and current can still flow through these lamps. So if this middle circuit gets burned out, which ones still go on? Which lamps work? Well, lamp 1 would work, lamp 3 would work, and lamp 4 would work. Okay? And that's because if you X this one out, you don't have to worry about the other ones going out. So now we say, okay, what is the current reading at lamp number 2? And so we know that the current at lamp 1 was 0.5. And so now we can determine, okay, well, what's the current reading at lamp 2? And this is where things for many people get a little bit dicey. If we use the exact same lamp, right? If we use the exact same lamp as we used in lamp 1, it's going to have the exact same current. Okay, so if we measured 0.5 amps here through number 1, then we're going to get the exact same amount of current through lamp number 2 because it is the exact same type of light bulb. So we get, we said 0.5 amps because it's identical to lamp 1. Okay, which means it's got the same resistance, all the same things. All right. Next, what is the voltage reading at lamp 4? Now, many of you were very, very good at figuring out the voltage of these two things. So we know that this branch is going to get 6 volts. We know that this branch gets 6 volts, and you know that this branch gets 6 volts. But these two guys are in series. So what do we do when two things are in series? Well, we have to split this up. So some of this energy, this voltage, is going to be used here. Some of it's going to be used here. And because these guys are identical, each of them is going to get 3 volts. So that was pretty good. I was pretty impressed when I was walking around. Each of 3 and 4 gets 3 volts. Okay? And if we want to draw a voltmeter, we know that a voltmeter needs to be drawn in parallel. Here, let's use a different color. And so if we're going to draw a voltmeter, this is how we do it. And there it is. And that was good because that was another thing we learned how to measure voltage and current. And so we know that we measure voltage in parallel. Okay, so that was the first page of this investigation. And check the next page. We're going to do the last example. This big one right here. We'll do the last example in part 2 of this lesson.